Okay, so the basic uh, form of what do I say, the neural network actually started out with multi-layer perceptron, basically. So that's the most basic one, and most of your concepts of convolution neural network, then recurrent neural networks, and the later ones can be derived from this. Okay, so so today will be more basics, and then next week onwards we'll go into more uh, deeper knowledge of transformers and all. Okay, so multi-layer perceptron. So what is that? So it's a very basic form of neural network where you have weights and you have biases, which are the trainable parameters that you train to get some probability value for your output. And based on your probability value, you are going to identify if it's a yes or no kind of problem, or if it's a So if it's a yes or no kind of problem, or is it a multi-class classification problem, or anything, or a segmentation problem? So segmentation is still beyond multi-layer perceptrons area domain, but still there's segmentation problems and all. Okay. So what is so how do you so let's take a use case first. Okay. So these kind of images probably all of you have seen. So this is the digit so this is handwritten digits, right? So for handwritten digits, and this is a very basic form, which is a 5 written in white against a black backdrop, right? So this is a grayscale image, right? So these kind of images are becoming will come as our input images or input to my model for training. Okay. So right now this image size is 28 cross 28, and each and every oh what happened? Okay. So right now we have a 28 cross 28 image size, and each of these pixels actually corresponds to a value between 0 and 1. And we call these as activation values. So whenever I'm talking about, so within the lecture, I'll talk a lot about activation. So you just have to understand that each of these pixels have a value between 0 and 1, and that's the activation. So when you have completely black sections, that will be 0, and the really dark light ones will be 1 actually. Okay. So now once you have now we are considering this as a numbers, right? Because your neural network can train numbers, right? So once you have activation for all these 28 cross 28 pixels, then you can actually make this pixels as 1 cross 28 cross 28 pixel values. So it's a single matrix which has a size of 784. Okay. So that basically becomes our input layer. Okay. Now what do you want to do is, sorry, if anyone, can you mute yourself, please? Yeah.
Oh, sorry.
Oh, Vishal, you are, yeah, can you please mute? Yeah.
Sorry.
Yeah. Okay. Yeah. So here you have 784 784 neurons. So whatever is my input, or all these circles that are kind of representing, is a neuron. Okay. So what is neuron? So in basic term, we will just call neuron is a thing that holds a number. Okay. So it will hold a number between 0 and 1. And then I have an input. So all those pixels now becomes my input of 784. And then I have some hidden layers. So hidden layers also have some neurons which have some random values to begin with. And then as you keep training these neurons, it will become some values with which will give you some output. Okay. So it will give you, so in the first round, in the first layer, you will not have anything that is of substantial use. in this like you won't get a really good value, because if you are trying to maybe train five and we give five images of five, it might at the first so in the first pass it might be giving you some random numbers which is not five, so it might have a very high probability or activation value for zero, right? So our goal is, as the models keep training, you will get a better so we will keep getting a better value so that it becomes more in line with what we are trying to train. Okay. So now comes the question is how do you think a neural network is training, right? So there's two things. We can conceptualize a training, and then we can figure out what is the real way it's training, okay, or what is actually happening behind the thing, okay. So if I am thinking, so in visualization terms, we can see that. So in general visualization terms, we can probably say that what is 9 and how do a neural network find out 9 and 8. So 9, we can think that it is given with, so it has a loop and a line, and 8 has two loops, right? So probably that's where the neural network is picking to find the differences, okay? So, so these, so actually, we can divide a 9 and a 0 into various different layers, middle layers, and then we can train on those. So that is what we can conceptualize is it is training on various sizes and shapes of this loop. Okay. But visit, yeah, so this basically training on different edges and patterns. So we can think that one of these middle layers is basically picking up on the edges of these digits, and the other hidden layer is actually picking up on the pattern. Okay, so this is a pattern like a loop versus a line, right? So it's picking up on that, and then and making and bringing in everything together is this output layer, where you get some values of activations, and based on the highest activation, that has the highest probability of that digit to be recognized. Okay. So now comes the concept of how is it doing it behind the scene, right? So has anyone worked do anyone know weights and bias, like how weights and biases are incorporated in a neural network or anything? Do you know anything about weights or bias? It doesn't have to be the right answer. Anything?
I have a basic understanding on the width. Like width is the amount of data that a particular neuron carries.
Mm-hmm.
Yeah, and
Okay.
I don't have much idea about basics of it.
Okay. Okay. Thank you. Yeah. Okay. So we can try to visualize this in terms of a very simple our equation. So everyone knows this equation, y equals to mx plus c, right? So that's our linear equation. So everyone knows about this equation, right? So let's look at this concept again. So here, that was my input layer, and then this input layer has to be somehow connected to my hidden layer. So the hidden layer 1. Okay. So how do you connect it? Like how do you get a value of this to begin with, right? So this is where this equation comes in. So I can, instead of y, I can say this is basically the y hidden layer 1. Okay. So this is one neuron, and which is connected with a weight. And so this is hidden layer 1 and I. I is the neuron, okay? And then actually uh, try to see. Okay, just No, it's okay. Let's work with this. I think all of you might not have access to the Teams has a whiteboard, but you might not have access to that. Anyway, so here, x, I am thinking x is my input and x is I1. Okay, so x of I, which means that any or x of, not x of I, oops. So y, oh, hidden layer 1, ith hidden layer is basically a weight into x, the jth input layer, okay, and then I comma j, okay, plus c is basically a bias, and this bias is applied to I, all the neurons in the hidden layer. Okay, so in the course of your training, what you are actually doing is you are modifying this value and this value, right? So, so this is how once you are modifying, what happens is my activation function for all these hidden layers are also updated. So you are actually updating. So you are updating all these values, right? So you are updating all these values of y, right? So you're updating these values of y based on values of wij, and this is your input layer that you already know. So I get these values from my pixel, and this is a bias which is also getting updated, okay, at every point, or every training step. So this is getting updated at every training step, okay. So if I go back here, so what happens is let's now think of, instead of those digits, let's think I want to train a neural network which can understand where my edges lie. Okay, so where are my edges? So you have given a image to your neural network with different edges like this, right? And which has a size of 784, let's say. Now, because as I was mentioning in my equation here, so Wij, what is the initial value of this? So initially, they are all random because I don't know anything about this. Okay. So it is a random value to begin with. And this from the random value is going to be a trained value. Okay. So it's going to become a trained value from your random, starting with random, it's going to become your trained value. Okay. So, so that is what exactly this image is telling you, that here when you are trying to train a model to begin with, you will have all these values as randomly appearing. And then as we keep training, our image will become like this. So more on the so because we are trying to find an age, so it should have all the random values coming into this point, concentrating on this area, and everything becoming black, right? Because we are trying to find an age. And a better approach is to have something like this. So have a green area along with some red section. So you have a very drastic difference when going from 1 to 0. Maybe red is really a very negative number you can put here, or very low number. Okay. So that's a very contrast, a very high contrast can actually make your model understand that this is where you can have a difference. Okay. Okay. So now going back, you can have a lot of weights which were randomly assigned some values to begin with, but these values can be really high. Okay, so a neuron, if I actually expand that equation, so this neuron, so if I try to understand what is the value of this entire neuron or activation value of this neuron, So what I can have is some the sum of all the activation values of this input layer, right? And then uh, followed by the weight value. Okay. So for each and every neuron, I will have a weight. So input layer A1 with W1, W2, A2, and it will go until N. So N for this situation will be 784 and Wn is also 784. And like that, if I have 16 neurons in my 16 neurons in this layer, the first layer, which is, 16 neurons in my first layer, then my size of W becomes basically, so W has a size of 784 into 16. Okay, so the W basically becomes size of 784 into 16. Okay. So the W for this layer, for the layer between, so this is between the layer input and hidden layer 1. Okay. Then I will also have a W between hidden layer 1 and hidden layer 2, which is of the size 16 cross 16. So I'm thinking my hidden layer 2 also has 16 neurons and hidden layer 1 had 16 neurons. Okay. And then at the end, I have an output layer. So hidden layer 2, comma output. And this size is 16 cross 10. So this is the number of weights that I will have in total when I'm training this model. So I have to tune all these parameters to get the right value of an image, right? For a handwritten image, for example. And then each and every section will have bias. So we'll have 16 uh, values for 16 neurons plus 16 plus 10. So these are all these values that are trainable. So all these values are called my trainable parameters. Okay. So these are called all my trainable parameters. Okay. So now where do I have it? Sorry, skipped it. Yes. So this is how you can calculate the number of trainable parameters, which is approximately 1300 for this small network itself, right? So you can imagine how big the language models are, which billions of parameters that needs to be trained. Okay. Okay. Now there is a problem with this kind of linear addition, okay, or in this linear kind of equation. What is the challenge? So because my weights are initially randomized, so I can have some weights, very high weights and very low weights, right? So and then when it is multiplied with A1, the input layer, you might have a very high value for some areas when you are multiplying it, and very low value for some other areas, right? So for some other sections, right? So this actually makes gives you some instability to your network, and this kind of instability is basically this kind of instability creates a problem, creates a big challenge, and your model cannot train with this kind of instability. So what you do is you make it you multiply with a function such that your values would be scaled between 0 and 1. So for this, you have a lot of functions. One is called a sigmoid, then there is called tan h, then there is called radio. Sigmoid and ReLU are the ones that you mostly use in this kind of calculation. Okay. Okay. So, now, what is the purpose? So we kind of understood what weights are doing right now, but what is the purpose of these biases. So biases are also my trainable parameters. But what is the purpose of a bias? The bias, actually, you can have a value of bias so that it gives you some meaningful value. So if I don't have a bias and I just have this value like this, like as it is, so what happens is it can become very high, but I only want something which where the value is above 10. Okay. So let's say this value is about 100 and minus 10. So this pixel or this neuron actually is contributing a lot to my so then this neuron has some significance during my training process. But if some neurons are calculating to be very small values less than 10, for example, I can ignore that, right? So those are not contributing. So as much as the weights you make it zero is good for me or good for my training purpose, is that we can safely forget about those or modifying those kind of weights during my entire training process. So my in the entire training process is basically two things that we want to do is figure out which are the weights that are or that are contributing maximum to my training model, and also eliminate in this process the weights that are not contributing much and we don't need to bother about it too much. Okay. So that's one of the reason you also introduce a bias. So to figure out that fine, this was a neuron that you which doesn't need anything like that, right? It doesn't need too much tweaking. So so in the training process, as the training process goes in, your model kind of gets an idea which neurons are needs to be tweaked the maximum and which needs to be tweaked minimum. Okay. Okay. So now now this is basically goes as your final equation. So you have A0, 1. So that is basically my, yeah, that is my hidden layer 1. And then, so A0s are all the activation functions. So I was mentioning about the activation. So now let's go back to those activation values again. So A00 are all those activation values that you already know. Okay. So these are known because these were the input values, right? And then, okay, yeah. So these are known because these were the input values plus a bias term that you have over here. Okay, and then yeah, and then it is giving back to the final A0. So sorry, this is the activation function for the next hidden layer, which is A1, right? So there were so let's go back to the neural network again. So we had two hidden layers over here. So first is this neurons, and then we have all these two hidden layers there. Okay. Okay. Then yeah. So then you can where were we? Yeah. So then you can arrange the weights and the neural networks. Sorry, the activation functions of the input layers accordingly with the bias, and multiply it with the sigmoid function. So you have uh, made the, what do I say? You have actually scaled the values between 0 and 1. Okay, that way. Okay, so now that we have all these things established in terms of a matrix multiplication, you can write it as weight and then activation along with those biases. And now that we have established this equation, we will go forward with the feed forward training. So what is feed forward training is simply equating this equation. So we will first, in the first training loop, we will equate this equation. So we'll have a random value of W, then some random value of A. So this is not random, sorry. This is a value of an image, pixel value of an image, and some random value of B. And then we will write a sigmoid function to make it between 0 and 1. Okay. So this goes with the, so this is your forward pass that we have for B and W in biases and widths, and you create a, so you get some values for widths and biases in the forward pass. Okay. Any questions until here? No? Okay. Now we will actually, so now that we did our forward pass, so what happens is after you have done a forward pass, let's say with 3. So we have used this image 3 and we are trying to now train our neural network completely. So after you did a first forward pass, you can see that there are some values, 0 to 9. And then there's a lot of neurons which have a high activation function. So it's not telling you for sure what is the value of this integer that is, or what integer that did this neural network uh, trained on or detected basically. So here you have a high value for 3, a high value of 7, 8 actually, right? But this is your original ground truth where every one of those values have a probability value or an activation value of 0 except for 3. So 3 has a high activation value of 1. So what do you do is now you have to, um, uh, yeah, you have to get a difference. So you cannot keep this trash, right? So you have to make this weights and biases tweaked in such a way that it will give you a good value for, it will give you values very close to the ground truth. Okay. So it can detect very well that this is 3, and so that it will have a value very close to this ground truth. Okay. So what we do is we take a cost value. So what is the cost? It is the difference between utter so it is the difference between the utter trash that it has detected, and also the difference of the numbers, like difference between the numbers actual ground truth value. Okay, so it's this is the basic difference that it detected over here, and then sum it up or get a square of all these values, and then we get one value for our error or the cost. Okay. Now, once you get the cost value, what we have to do is now minimize the value of this cost function. So cost is basically a function of all the widths, and we need to minimize this function. So all of you did remember your maybe 11th, 12th maths on inflection point or minimizing a function in like regular calculus. Anyone remembers that?
Yes.
Sorry.
Yes, ma'am. Yes.
Yeah, yeah.
Yeah, you remember, right? So, so what do? You take a derivative, right? So if you want to minimize your function, you usually take a derivative, and then you calculate if it's moving to the left or moving to the right, and uh, so basically you want to reduce your tan value, right? So the m value, right? So it reaches your minimum point. Okay. So let me look at this equation a little bit. So we are trying to find the slope. So we are going to find the tan theta value or the CW value after you did uh, a derivative, after we are taken a derivative of this value. So is it moving to the right or moving to the left? So shift right, negative slope, shift left, positive slope. So after this point, so if this is the minimum point we are trying to figure out, so you can shift it left or right based on the slopes that you are getting. Okay. So now we have here in this situation, we are considering W to be one value, okay, just one value. But what we can also do is make this value. However, W is not only one value. So remember, W and weights and biases, we have around 13,000 parameters. So what you have to understand is you have to minimize all these 13,000 parameters so that it gets the right value for your digits, right? So this value is minimized. So if you can minimize all these weights and biases parameters, then here your values are minimized and it gets this and it reaches this ground truth finally. Okay. However, in reality, when you are training a model, it's never possible. But our goal is to make it go to some local minima value. If it has really reached to some local minima value, then what happens is your yeah. So what happens is you get a good fit for your widths and biases. So our goal is to make this yellow point come into some of these minima values at least, so that this kind of trend to this ground truth. So it kind of goes to this ground truth value. Now the problem is, you see, when you are dealing with a one-dimensional problem, okay, fine, maybe my weight can lie between -8 to minus +8, okay. But when you are dealing with 13,000 parameters, it's very difficult to have uh, a range for all these parameters, right? So you have to find a range for all these parameters. So it becomes a million different parameters to find, to match, right? So that is a very challenging problem it becomes there. So what you do is you take use of learning rates. So what are learning rates? So because let's think of it, instead of that one-dimensional problem, now let's think of this as a two-dimensional problem. Even though it's a 13,000 dimensional problem, we will actually now consider this for our visualization purpose, this to be a two-dimensional problem. So we have a small, we will select a small learning rate, and each of these small learning rates will go in steps, okay? So it will move in small steps. So you can think of this as you are trying to climb down a cliff, a mountain cliff, right? So your cliff can be a rugged terrain, right? So you can have bumps and no bumps, like so some of the sections will be, or let's say it's a tall cliff, and some would have a very steep slope, some will have a gentle slope, right? So if you are trying to climb down the cliff, you will try to follow the path of a gentle slope so you don't trip over, right? So that's the same situation when you are trying to find your minima value. When you are trying to find a derivative at the minima value, you are also trying to find a value where your parameter doesn't trip like that, okay? And take steps, a certain step at a time. So usually it's a good idea that you always try taking uh, a certain step. So let's say this is maybe a small step. To begin with, you can have a very small step at a time, and that is called learning rate. So at what rate is this curve in, and in which direction is this curve moving? So to find the right parameters which will minimize my weights and biases value. Okay. So that's what you have to do, is think of this as the you're climbing down the cliff, you taking small steps at a time, and you are also trying to not move in one direction, but you are trying to change your direction all the time so that you don't trip. So this is exactly what your when I'm training a model, your parameters are falling like that or following a path like this with small steps at a time in some direction, but it's trying to always trying to find the minima value. So if it's shifting left, negative slope, slope. Shift right, it's a negative slope. Shift left, it's a positive slope. So you're trying to find the minimized value based on a learning rate and then calculating these values at every step. Okay, the learning rate will help you finally to reach that minimum value in this two-dimensional space. And now you can think of this two-dimensional space to be in more like two-dimensional space to be 13,000 space. Okay. So this kind of situation is basically known as your backpropagation. Okay. So in your backpropagation, you are taking the derivative of the weights and trying to find the minima value. So in many job interviews, you would be asked that what is a backpropagation. So when you train a model, the forward pass and then you have a backward pass, because in the backward pass, you are training all your weights and biases values. Okay. Now we want to think this in a different way. Because I have 13,000 parameters, you cannot think of this in a two-dimensional space, right? It's very difficult to figure out that. So what I will do now is I'm thinking it in terms of weights, in terms of matrices again. So let's think this in terms of matrices. So I have all these weights and biases. I'm writing all these weights and biases with W with an arrow sign. And this, and then delta C. So delta C is the cost function that I want to minimize in terms of all these W values, have some values, right? So if I see some of these weights have a very high value and some have a very low value and some do contribute very less or very less positive or negative value, then what I can safely kind of presume is those high values and those really low values are the ones which are really contributing a lot or which needs to be lot of nudging or a lot of tuning for tuning to be to go to this or to go to the right weights, okay, or to become the right weight. So my model will be more focused on these sections, okay. So for example, minus 0.51. So this value over here, it's a very let's say it's a quite a large negative value, because if I'm thinking my values between -1 and 1, then it's quite a large negative value and I need to be careful about tuning this value. So it's contributing a lot to my tuned parameters or my tuned weights and biases. Okay. And then finally, yeah. So this is, so should increase somewhat. So if I'm tuning, so if it's a high value, and yeah, so sorry, if it's a high value and I need to tune it more, if it's a low value, if it's a very low negative value, I have to also tune it more. If it's in between near to zero, then it needs a somewhat tuning, a little bit of tuning. Yeah, so that's so these are some things that just to give you an example. So the signs mentioned in the input vector should be nudged up and down. So the signs, if it's a negative sign, then we have to nudge it to negative. If it's a positive, we have to nudge it to positive. And the relative magnitude mentions which changes more. So in short, which weights matter more based on your relative magnitude of this sign. Okay. Okay, so just some things to remember before we close this section, and I'll give you out a small assignment. But the main homework is for you guys to complete that. So for this week, you would complete the GitHub repo, upload your codes, and also keep the weights and biases. So I will share that weights and biases link in the WhatsApp group after this call. So, but the main thing to remember, just going back, is to remember that cost function is average of all the training samples. When network is learning, it's minimizing, trying to minimize the cost function. The process of nudging an input with positive gradient of cost is gradient descent. So this is called a gradient descent. As you see that it is descending, right? So you're trying to descend it to local minima and maximum. It's a way of converging to a local minima of cost function. Okay? And finally, you need to remember that which are the signs kind of tells you which needs to be tuned more, which needs to be tuned less. Okay? And the relative magnitude mentions which changes matters more in this situation. So finally, we now have understanding of a multilayer perceptron. And then when you actually try to find after few passes of training, you are trying to now get a value of all the weights. So, and you are trying to plot it, you will see that all the positives and negatives are taking some kind of random patterns, but they do take a pattern because with fine more tuning, all the negatives and the positives will now keep clustering more and more. And then it will try to find, maybe this is trying to find a six or something like that, right? So it, as your training goes further, your weights will converge more to a pattern very close to the digit that you are trying to identify. Okay. So it usually doesn't really finally depend on your so so what we thought in the beginning, like where does it uh, find the age and the pattern? It does find the pattern, but it doesn't really try to understand the ages. It's what it is trying to understand is all about these weights. Okay. So what it is, what a final neural network is focusing on is all these weights. So do I have to nudge the weight high up, or I have to nudge the weight low, or I don't need to nudge the weight, or what is that nudging? What is that tuning that I need to focus on? Okay. So finally, okay, so this is a trick question. So if I have trained a neural network on some digits and then I use this for my output, for my input, then what do you think will happen? Will it give you something? Can it give you something useful? I have a neural network which is trained on all digits, but in that neural network, I'm feeding this image. So do you think you'll get something useful out of it? Will it give you some good output? Yes or no?
No, ma'am.
It will not, right? Because it was not trained on it. Okay, cool. So I think this gives you the basic stepping stone. So next week we'll start talking about RNNs, recurrent neural networks, which are kind of the precursors for all the language models that you have these days, right? Or right now, all these language models happening. Okay. So I let me give you. Hello, Vishal, you are there?
Yes, yes, I'm here.
So I think so this is the first class. So next class, let people join and give
No.
yeah, their GitHub, and I will share this link so they can follow how to upload to GitHub and weights and biases. And in the next class, guys, please whoever is joining, please show your codes and give a little bit demo of that, and then just a minute, stop the recording. Yeah, then give a demo, a small demo of